involves theoretical work and experimental work. Some of the people are named here. On the theory side is Sophia Konomo, who's joined our group recently, the postdoc Dmitry Solanov and myself. The integral experimental group involves Dan Garman and Ella Bracker and Sam Carter. I should say that in addition to the quantum dot work, we're particularly interested in impurity states, and especially in impurity states in diamond, which is an opportunity for higher temperature solid state quantum information. But I'll talk mainly about quantum dots for the moment. And I'll talk mainly about two things, potentially of interest here. Basically, qubit gates, single qubit rotations and 2-qubit gates. So let's take a look at this system. Spins are, in a sense, natural qubits. You have two states in the magnetic field. Quantum dots are particularly advantageous because you have a large optical dipole moment. And these things are tens of nanometers in size. So you couple really strongly to them with an electromagnetic light. The coupling occurs because of an excitation of an electron-hole pair. The hole is from solid-state physics. The hole is the actual magnitude of spin 3 halves, but it acts like a spin 1/2 anyway. The strong coupling makes it possible to make fast optical manipulations, nominally on the order of tens of picoseconds, for example. It's also been discussed a lot, often believed, that these systems are potentially scalable and integratable into solid-state materials and technology. The coherence times are relatively long, but that may be of the order of a microsecond, which is long enough for 10 picosecond pulses. Oops. Okay, the kinds of quantum dots we're talking about are typically indium arsenide quantum dots, growing by molecular beam epitaxy on gallium arsenide. They grow up into dot regions because there's a strain mismatch, there's a lattice mismatch at the surface, and the dot forms. And that's all pretty well known. Many groups have learned and shown that it's possible to control the charging in these dots with electric fields from Schottky barriers and NPI structures. One can also generate various optically induced states and look at them in photoluminescence. And there's been a lot of work done on the physics of these systems. But what I'll talk about a little bit is spin manipulations and spin gates in these things, starting from some work some years ago in our group, but going up to what's going on at the moment. These quantum dots are anisotropic in the sense that they're a little bit flat. So there's a natural direction, a growth direction for the spins. And that's typically the optical axis as well. And that's shown here. Now what you want to do is make manipulations in this subspace. But the energy separations there are quite small. The energies being on the order of microwaves. So that's too slow for this kind of a system. So one looks for excited states and looks for things like the lambda system. So one can do circularly polarized lights on these systems. These are total energy pictures. You have spin here, you have an excited state of the 3 particles, which is often called a trion, the 1 hole and 2 electrons, as an excited state. Well, that's fine, but of course the optical selection rules go only up this way and then come back down and don't access this state. The standard way of solving that problem is just put a small magnetic field in the void direction along the surface of the sample. And that mixes the 2 states along the optical axis and allows for these selection rules to occur so that you can reach both of the ground states, so to speak, through the excited state, and it gives you a kind of lambda transition for the systems. Okay, we've been looking at how to control these with optical pulses for a while. Some of our work was sort of stimulated by one of our people, Sophia Konomo, noticed that there was some pulse shapes which were exactly solvable, analytically solvable, and she became interested in those. They typically have the form of like a hyperbolic secant form, which when you actually look at real laser pulses, it's interesting, they're very much like it. To look back at that at times. It was shown in the 30s, but for a 2-level system, that the matrix of that problem could be solved exactly by this sort of pulse shape. And it had certain desirable features. If you put a pulse of 2 pi intensity in it, take it up through the excited state and back down to the ground state, it left no excitation in the excited state. And that's a question about fidelity of these states. The other thing is that it generated a phase in the ground state. That's not terribly interesting in the two-level system, but it turns out to be an interesting issue when you try to solve the semiconductor problem. The semiconductor problem is shown here. One has the optical excitation from this ground state to that excited state. But unfortunately, one has the mixing of the magnetic field, which mixes the ground states. So it's not quite so simple as a two-level system. On the other hand, if you think of a fast optical pulse, then faster than the time that the mixing occurs here, and one can think about this transition occurring and then think about solving the problem that way. So in that sort of zeroth approximation, one can solve this problem, and what one obtains is the same sort of characteristics that one saw in the two-level system, namely a 2 pi intensity pulse will move the state up into the excited state, back down, and leave no excitation in the excited state. In addition, a phase is generated in the ground state here, which depends on the detuning in this transition. And that's fairly interesting, because we now have a different kind of system, where we have a phase in this system, phase in this ground state, and not in that ground state. Well, that is equivalent to a rotation around the optical axis, which is what we're trying to generate. So this will do that kind of thing. Now that's fine around one axis, but you need transitions around, need rotations around various axes. One can generate those in the same sort of way. It turns out if you look at linearly polarized pulses in the x direction, they will access both of these kinds of transitions. And if you use a broadband enough pulse, then you're hitting both of the transitions. But the key here is that the transitions are of different energies. So it generates different phase shifts in the ground states. And the difference of those phase shifts amount to rotation about the x-axis. Okay, fine. So now we have both things going. Now, of course, we've done the full calculations, full density metric calculations, but a hand-wavy way that I presented it here. And we find that the main losses in these systems come from electron-hole recombination, which is an endemic problem in the solid-state systems. So we put that sort of thing in. And we find fidelities in these gates, times of the gates which are tens of picoseconds, fidelities reaching 100%. And one can make rotations around arbitrary axes. Well, that's all fine. It's theory, it's fine. What have you done for us lately? And so we got involved with an experiment with the University of Dortmund to demonstrate these sorts of things. And what you're seeing here is an array of quantum dots where a pi pulse moves an electron state up here, or more precisely creates a coherence. You can card an electron state down here, which then rotates around the white magnetic field, which you can picture in a block sphere with the magnetic field going this direction is rotating around that way. Okay, fine. That's exactly what you see in this curve here. The spin is rotating in the plus z direction, minus z direction. Here it's in the minus y direction. So at that point where I pointed to is actually the minus y direction here. So now one can put an additional control pulse on, control pulse here, so the thing is here, and affect the rotation around this axis, which I showed before. If it's a 2 pi intensity pulse, and it's at 0 detuning, it will rotate all the way around here and be 180 degrees out of phase with what it was. If you look at this trace here, you'll see that it's exactly 180 degrees out of phase. That's fine. The rest of these curves are for increasing amounts of detuning from that optical transition. And if you plot out the angle of rotation as a function of that detuning, it follows exactly the relationship that we obtained from that model. So that indicates that things happen pretty much as we expected. Okay, well that's all fine and good. We have single experiment. How did I do this? The big problem is at least 2-qubit gates and multi-qubit gates. And we've been thinking about those things. Now, a natural thing you might think about to create a 2-qubit gate is that you need some sort of interaction between the qubits which you can turn on and off. So we can think about our atomic physics friends and think, well, maybe we should have a cavity, in this case a microcavity, which exchanges a photon between the two quantum dots and couples them together in that way. And we might be able to use lasers to turn this thing on and off. That's the way. The difficulty in this game is that such cavities don't exist in a solid-state environment, or didn't at that time. The problem is that you couldn't get coherent, strong coupling for these kinds of systems. And the main problem, I'm talking about maybe a dozen years ago now, that the main problem was losses in the cavities. These are dielectric optical cavities, and there are too much losses in the cavities to sustain strong coupling. Effectively, you need a situation where the exciton-photon coupling is stronger than the losses in the cavity, both to the exciton, the optical transition, but also and mainly due to the cavity itself. Okay, so we got involved in collaboration with a group at the University of Würzburg to try to address this problem, along with any number of other groups, many of them participating in the DARPA program in the US. And this took quite a while to get taken care of. I'll sketch out a little bit what happened here. It was really a tour de force of fabrication. Theory didn't play all that much important role. It mattered, what we found is we had to make very, very high quality cavities. Or at least they seemed very high quality at the time. And getting the masses up quite high. Another thing is that we wanted to make bigger quantum dots. This is one of my few suggestions in this area. And that helps too. The kind of results that we obtained out of that are shown here. This is photoluminescence for quantum dot in microcavity. It's shown as a function of temperature. Why temperature? Because the cavity modes are relatively insensitive to temperature, but the quantum dot modes are quite sensitive to temperature because you change the bandgap of the solid. So you see here, the cavity modes aren't changing very much, but these guys, the quantum dot modes, are moving through the cavity mode. And what you see right here is the anti-crossing from the strong coupling, coherent coupling in the system. That was basically the first time that this was seen. And subsequent work is shown on the right-hand panel, where you see the same sort of thing. You see a cavity mode here, but you see in this case two quantum dots going through that cavity mode. If you look in this region, you see 3 lines. So here we have 2 quantum dots within the homogeneous line of the cavity mode, which means it's possible to do coherent manipulations between these things. This stuff came out in the 2005 timeframe, and shortly thereafter, any number of groups around the world implemented these things as well in different cavity structures. So now it's readily available. We have photon crystal cavities, blistering gallery laser structures, and so on and so forth. So that, one might think, would have brought us to the point where we can make some progress on the 2-qubit gate problem. It's hard to believe that that's already 7 years ago. It seems only recent. But basically, the 2-qubit gates along that sort of line have not been demonstrated to date. Nor, for that matter, has a clear design for how to do it, which satisfies all the reasonable requirements that one might want been put forward. So let me tell you a little bit about what we're thinking about along these lines, and an idea that we think we have which should work. We think it will work. Okay. It's theoretical. The idea here is that we have another one of those cavities. This happens to be a picture of cartoon photon crystal cavity. So that should have confined photon wells in that region. And we have in mind to put 2 quantum dots into that region. And then have the quantum dots exchange this photon well and use it as the dynamic link between them to the gates. We have, in making the gate, we're always looking at this long-range physical interaction that you can control. And then if you're lucky, you get into a system which is scalable and so on and so forth. Now what we're aiming at is effectively a phase gate, which is that we wanted to change the sign of one qubit to come into emission of another qubit. And it has to be compatible with one qubit operations in the system in order to make a universal set of operations. Okay? This is the idea here. What we have is two quantum dots, one here and here. Each of them has an electron and a void magnetic field, and that gives you the splitters. Here's a trion in the excited state again, and void magnetic field. Notice that the energy of the two are different. There's a lot of discussion in the early days of putting quantum dots about the need to make them all identical. I was hesitant about the need for that at all when we started talking about it. But as you see here, it's actually a magnitude. Anyway, we have the two quantum dots, and we have the cavity, which can sustain various photon folds. It's all in a void magnetic field, as we had before, for much the same reasons. Hamiltonian is there. All the standard terms that we also have in mind. Use a classical laser to control these things. Now this picture looks a little bit complicated. It's really where all the action is. Let me kind of walk through here. What you see is everything is a function of the frequency of the cavity mode. So let's look down here at the qubit states first, which are written out over here. These are two spins and the two dots. Put a spin in each dot, trust me, you know, working that way. And you have four states which span that manifold. Two of them are degenerate because they're far apart and not interacting. Okay? Now we also have a trion here, which is the one quantum dot with an excited electron hole parity. And then here's the other quantum dot with excited electron hole parity. Here's the cavity photon, one cavity photon mode. Here's a two cavity photon modes. In addition, we have here one trion plus a photon and another trion plus a photon for the other quantum dot. That's more or less how the picture starts. Of course, what you're going to see is that there are interactions and anti-crossings where all these things are occurring. It's fairly obvious here, but it gets even more messy here with a variety of things occurring. Okay. That's all drawn out over here, and the states are written down somewhat carefully. What you see here is this first anti-crossing corresponding to one quantum dot. Here is the anti-crossing corresponding to the quantum dot. This is the ground state manifold. We call that ground state or whatever. We call that the one particle manifold. Up here you have two trions or two photons, or one trion and one photon. And we call that the two particle manifold. And that is what we have designed the two qubit gate based on. Okay. It's important that the structure be able to sustain at the same time one qubit operations. That can be done in more or less the same way we did before, which is to have fast operations. I should have perhaps made clearer on the last slide that what we found as a practical matter in doing the calculations is that the effects of the photon coupling in the single particle manifold were found to be relatively small. And that gives us an option to sustain one qubit operations here. The effects of the photon coupling in the two particle manifold are larger. It's partly by the way we choose the parameters. But that gives us an opportunity to run the two qubit gate there. So, go to this slide, and now we want to think about the one qubit operations. If the pulses are faster than the interaction generated by the photon, then it effectively acts on one spin alone. And if you look closely here, the energy of the excitation from this state to this state, which simply puts a trion where that one spin was, and the energy of this state, which has the same upspin here but a downspin on the other spin that's not being acted on at the moment, are pretty much the same. And more precisely, they typically lie within a homogeneous line of transition. And therefore, you're making a transition on the first spin independent of what the other spin was. So you're generating a single qubit rotation in this way. And in effect, what's happening is that you generate a lambda-like situation where you go up there and down there just the way I explained before. Now what we want to do is to have a two-qubit operation, and we're interested in a phase gate for that. But we need the single qubit operations in order to make a complete set of things. The phase gate we have in mind is simply written down here. It's a matter of changing the sign on one of the basis functions. If we can do that with a series of pulses. And what we designed here is a way to do that, and not detailed calculations for it. What happens is that we make one fast one-qubit rotation, a slower entanglement pulse, and another faster single-qubit rotation pulse. And that's what this slide does. The first pulse takes the system, just as I explained before, one qubit state, it excites the spin up into that state, and leaves it there. When the second pulse comes and moves the system up to this state, and the two-qubit manifold and goes down there, it's 2 pi pulse. And the third pulse takes the system down to ground state. And we argue with the appropriate phase changes. It's a little bit hard to see everything here. The phase changes are sketched out a little bit over there. What's happening, in fact, is you're taking those two states, which I pointed out, with a single qubit rotation, moving them up into this excited state with a pi half rotation, which gives you a phase minus I on each one. But then we arrange it in such a way that only this state participates in that entanglement operation. So that one goes up and comes down, and then both of these things come down again, and these are not in resonance, so they don't participate. So if you add up all the phases here, you have in this one minus I, minus 1, which is 1. If you add these up, you have minus I, which is minus 1, and nothing happens to those guys. So that's effectively the phase gate. Here's the pictures, which are complicated. Trying to figure out what way to go. We've of course made full calculations of this thing, rather than sort of handwriting arguments. And I won't go through all that. But as a part of the full calculations, we're addressing the question of fidelity in the system. There are two kinds of losses in the system. One is losses due to unwanted coherent dynamics, which are off resonance. There are lots of transition there, obviously. And those pulses are affecting all those transitions. So you have to take into account all of those transitions. The second kind of issue is that there are true losses. And those losses come from electron hole recombination, and come from losses out of the cavity. Cavities have finite Q. So we've done all those calculations, and here's the fidelity as a function of the finesse of the cavity Q, and effectively the electron hole recombination. What you see is that there are wide regions where you get fidelities higher than 90%, which is pretty good in a solid-state system. In addition, we are interested now in trying to, I should say, raise the quality of this gate and use things like pulse shaping and so on, and choosing parameters better and more accurately to increase the fidelity of the system. The experimental people in our group are very much interested in this kind of thing, using both the structure exactly the way I suggested it, and a structure a little bit different, which I'll tell you about in a minute. So that's pretty much the story of the photon-induced two-qubit gate. I'm going to make a couple of comments about it. There's a couple of characteristics of it. One is you notice that one doesn't have to have the excitation energies of the quantum dots the same. This is an enormous discussion at the beginning of the quantum dot implications of quantum information. And people spend a lot of time trying to figure out how to make identical quantum dots. This we see as an advantage with respect to scalability, because you can use one photon mode with appropriate lasers and couple a number of different quantum dots in the system. And one can show that explicitly. The other point is that these cavities contain a number of confined photon bonds. So that the combination is that one, if you're a theorist or an optimist, you can think about this. Theorist, I mean. You can think about putting a bunch of these quantum dots into a photonic cavity and using a classical laser to impact them. And as I said, one can use each confined photon mode to couple a number of quantum dot pairs therefore they're different from fine photon dots to couple together quantum dots. If you think about it practically in terms of parameter of the system, there's not going to be too many, half a dozen maybe, in one of these cavities. But it's very easy to have a waveguide of these photonic cavity structures and communicate between these sort of nodes. So that's an interesting system. In that sense, it offers possibilities about scalability. In the last couple of minutes, let me tell you very briefly about something quite different. It actually isn't quite different at all. You see, there's a strong resemblance to what I just talked about. It's a different physical system. We've done a lot of work theoretically and experimentally in this system. For the moment, I'll just tell you about a recent experimental result, and just in a sketchy way. I'll give you the reference to the details of what you can see. This system it deals with these so-called quantum dot molecules, which are very popular. We've done a lot of work on at NRL. It's possible to grow these quantum dots quite close together. It's also possible to draw quantum pictures. But what happens here is you draw one quantum dot. This quantum dot is constrained by strain in the system. The next one grows naturally on top of it, so that these are not that difficult to obtain, especially after we've worked on it for a few years. It's also relatively well understood how to charge these systems using Schottky structure or other structures, and how to control the optical states of these systems. As I say, a lot of work is going into it. Now let's think about them for a minute in terms of gates and the kinds of things that we're talking about. This is really a different kind of system. We have an interaction between these things. It comes from the tunneling interaction of the wave functions themselves. But it's odd in the sense that it's always on. There's no way to turn it off. So you have to think about the gate in a different sort of way. But anyway, it's an interesting system, so I think a little bit about that. Now what the system looks like is that you can think about the left and the right quantum dot, if you will, and put spins in them. If you put a spin in each one of them, then the ground state of the system is actually a singlet of these spins, like so in the two quantum dots, and then three triplets at pretty much the same energy. It's not a spin up and spin down, it's these things. In addition, the optical selection rules go from the singlet to this communal excited state, so to speak, and the triplet of that state. So now you have access between singlet and triplet through this common excited state. It's also very interesting in the subject matter that we talk that there are other triplet states here, which are part of this manifold, that are not coupled by these optical transitions. These can be used to initialize or to read out the spins very in structure. Let's concentrate on the middle for a moment. One has in here effectively a Raman transition. So it's perfectly possible to use the singlet to pump the triplet shell states there in the traditional way. And that sort of thing we've done quite a bit of. I say we and experimental. All of this group that I'm talking about, the theorists, experimentalists, are part of a larger group that I take care of. So the exchange here is actually a kinetic exchange, which it simply means that if you have a singlet state, the electron can't tunnel back and forth. But if you're in the triplet state, it can. That's called a kinetic exchange. I'll say I'll tell this story rather briefly. The same sorts of ideas that we had before. What one can do is think about the states of the system in the clock sphere. Think of the singlet there and the triplet there. Now it's possible to use, again, the short pulses, tens of picoseconds, and impact only one of the spins. So one can add, for example, a phase to one of the spins there. Suppose that one adds the phase times 1. It's pi. And that moves you up to the triplet state. So it means that operation effectively includes that sort of rotation. What I'm thinking about here is a broadband pulse which includes both the single and triplet state. Spirit is the same thing as what I talked about before. Now what you can do is instead of moving it all the way up here, you can move it up here, pi hands rotation. What happens now? As a matter of fact, it precesses around this way, this block sphere. That's because of the exchange interaction. These are no longer the eigenstates. So it's going around that way. Now you can do an experiment in which you move it up here, let it go around, you get it here, and then move it up there. Or you can move it up there, let it go to the back, and then move it down there. And that's as a function of how long you let it process there, how long you wait to put these pulse in. These experiments have all been done. These are Ramsey fringe experiments, they're absorption. Trust me, those things have all been done. Now let me tell you a variant of that, which is quite interesting. We can have a broader band, we can have a narrower band pulse, a slower pulse, which then now hits only the singlet state. This is very much like the single qubit rotation we talked about a moment ago. Remember, we have lots of planets that set plus SL. Now we just have the singlet and triplet of this block sphere. It's the same sort of thing. That involves a rotation around the hemisphere of this block sphere. That's interesting. See what we can do with it. What can happen is that you can go through the same sort of thing I described here. Move it up here, let it go there, and then put this broadband pulse on it, and speed it up or slow it down. That's affecting it. And that's the heart of the gate. Let me show you how that works. It looks an awful lot like what I described before for the photonic tether. As I said before, when it puts one fast pulse on it here, then a slower pulse here, and a fast pulse there. That's the pulsing sequence. And now you can put various phases onto the system, and that phase can mean various kinds of gates, the squared and swap gate or whatever. But the physics of the thing is that you're speeding up and slowing down rotation around the block sphere. And what I described in the last class is effectively this: you go up here, speed it up, or slow it down, the same sort of thing. These are Ramsey fringe experiments, which are a little bit hard to understand exactly what's going on there. But they demonstrate the kind of thing that I just described here. And there's a reference there to a recent Nature Physics paper that came out with the details of this. I'll just make one comment and here. The comment is simply this. It's a lot of information. We've also been interested in using whole spins as qubits. The reason for that is that a chronic problem in the solid state environment is hyperfine coupling to nuclei. Well, it isn't a chronic problem, it may be a tremendous advantage for quantum storage, and that's the thinking critically about that, and actually doing work along those lines. But holes, there's a certain kind of decoherence that comes about because of nuclear coupling. If you look at holes, the nuclear coupling is small. It isn't zero, but it's small. This again is a band structure effect because holes come from these states. And so, whoops, it's totally spontaneous. In any case, these pictures here are just to remind me to show you that many of the things that I've been talking about and some of the other things that I've not been talking about with respect to these coupled molecules, we've done in for whole qubits as well. So that's pretty much my story. We've talked a little bit about spins and quantum dots, spaces of quantum information, single qubit operations, 2-qubit phase gates, entangling gates, and a couple of molecular structures. As I say, we are interested both in the quantum dot situation and also in the impurity and decentered diamond situation. We're moving, we started actually out with the decentered diamond and moved into a lot of work in quantum dots. I think we have an interest in going back to the decentered diamond. Many of the things I've talked about, analogous implementations for the decentered. And so I think that we're interested in that as well. And that's my story. Thank you very much.
Is there a way to rotate the two triplet states
Yes, I haven't thought a lot about it. Let me make a related point. If you think a little bit about this system, the part of the, I mean, for reasons of presentation, the part of the thing I was talking about is not the complete building space of the problem, okay? And you really want to, as I think you're suggesting, access the whole building space here. And the way of doing that is not very difficult at all. It's exactly what I said before. You put a void field on. Right? Put a void field on, and then the optical selection rules go this way, this way. You have a bunch of lambda transitions in here, and you can now make interchanges between those. And we looked at that in at least two respects. One, not so far in trying to control all the rotations of things yet, but the most important and interesting thing is that because there's a tiny interaction down in the ground state, it's probably in the API, you can use these transitions to monitor, either to initialize the state or to monitor the state that you get in a non-destructive way. Because the state is in here, there's a weak interaction there, you can sort of monitor what's going on through that auxiliary state. So the longish answer to that is that's all part of one building space. The way of getting it all